We're going to continue what we started back on Thursday. This is going to be transformers. And kind of remind yourself of the way that we approached it. The first thing we did is we said, hey, there's this operation called attention. Let's build it up. Let's understand it. Let's motivate it. This was just kind of a fixed mathematical operation. It really just has three inputs. Those were these matrices, the key value and query ones. And then we said, OK, from this operation, let's build an attention layer. So we're talking about something that we're actually going to put into a deep learning model. And then after that, we said, OK, we're going to build these further into an encoder unit, and then finally build this whole model called a transformer. We're going to keep talking about that so we can get to the end. And then we'll very briefly talk about something that doesn't use attention directly, but is still very promising for building a powerful language model. We're going to call these architectures subquadratic because of this property that they're more efficient than at least a naive transformer would be. OK, let's do a little bit of logistics. OK, so I've started putting recordings on Canvas in Kaltura. You should be able to see at least the previous two lectures. I'll keep doing that as we go along. If I forget, please remind me to make sure I upload. All right, so we're going to finish up this architectural component today. On Thursday, we're really going to start talking about different language models. So the thing that's happening today is that we're almost entirely talking about the original transformer, which was specifically for translation. It wasn't a general foundation model. It just happened to be the case that you could use parts from it to build very powerful foundation models. We'll be doing that on Thursday. We'll actually spend a couple of lectures on how you take all these elements and create modern language models. And then in a week or so, we'll start talking about prompting. We'll talk about taking our pre-trained foundation models, improving them, specializing them, adapting them, and so forth. Any questions about where we are as a class? All right, if not, let's go ahead and jump into today. The first two pieces are exactly what we saw last time. So we're going to do a very quick, very brief review of the way we built the attention operation. And then we'll keep talking where we stopped last time when we ran out of time. We were starting to talk about the transformer architecture overall. We had gotten through talking about an encoder unit, and we were about to talk about a decoder unit. And once we have those two things together, along with some extra pieces at the end, we pretty much have a whole transformer. So we're going to finish that today. And then we'll talk about kind of the intuition for these new class of models. These ones are called state space models, but there's actually a lot of variants as well. We're not going to have time to go too in-depth, but this is a pretty good area for folks who want a paper for their presentations or want to try something else for their projects. Questions or anything else you guys want to ask about? All right, let's start reviewing in that case. OK, so the starting point that we had was this retrieval system intuition. And the reason why we tried this is we said, OK, we want to understand the way that elements in a sequence, and especially words and sentences, the way they interact with each other. We said that this is going to be necessary for translation, but probably also for any other language modeling task. And we had this very simplistic idea. We can take, for example, a search term like this sentence over here, what restaurants near me are open at 9. And we break this into a query and a key. And this query and key give us some potential values that we might want to take into account. They create a score, and based on those scores, I can look at these different values and say which ones are more important, which ones are not, or I can combine them or what have you. OK, so we had this very vague intuition, and then we went ahead and translated it into an actual mathematical operation. What we said is our starting point are going to be these word embeddings or word vectors. And what we're going to then do is to create from them 3 different vectors. So every single word in the sentence that we're operating on is going to get its own word vector, 1 per word. And then we're going to take those 1 word vector per word, make them into 3 things. And those 3 things are produced from linear transformations. They're just going to be matrix multiplications. We have 3 of those matrices. The query matrix, that's that WQ, the key matrix, the WK, and the V, which is the value matrix WV here. So you take these 3 matrices and you multiply them for each of our words x1 and x2 to produce Q1, K1, V1, Q2, K2, V2. And of course, if our sentence is longer, we produce more of these guys. All right, everybody's comfortable with this? Cool. OK, we said that there might be other ways of doing this that don't have these exact 3 terms, but there's probably a pretty good reason for why we have these guys. We also said that for these embeddings, for now we're pretending that we have them, but when we actually go train our model, we're really going to train them along with the rest of the model. So what we're really seeing here is a lot of the weights, a lot of the parameters in our model, these matrices, they're weight matrices, but each of the embeddings, those vectors, are also trainable weights. And we're going to train this whole thing all together at once. All right, everybody comfortable with that? Okay, one more thing that's sort of not quite correct about this simplified picture. We don't really operate directly on words. We normally have this additional layer called a tokenization approach. And this thing translates raw text into a sequence of tokens. The tokens are the basic units that you work on. And these things are fixed. They come from a vocabulary. A typical vocabulary might have 50,000 tokens. So really, we're not working so much on these word embeddings as much as token embeddings. But from this kind of simplified point of view, there's no big difference. Sound good to everybody? Cool. All right, so we're going to do some operations with these guys. We're going to do exactly the equivalent of that simple intuitive retrieval picture that we had. We said we're going to compute a score if there's a good match or a good alignment between the query vector and the key vector. Okay, so this is just the example that we had before. There's lots of ways that we could measure alignment between query and key. We're going to do it in the simplest way we can. It's very efficient. All we have to do here is do a dot product. So things that are well aligned are going to give you a higher magnitude, and things that are not very aligned are going to give you, something closer to 0, or things could be aligned the other way and give you a big negative, etc. Okay, so this is a dot product. For this reason, this is often called dot product attention as a result. There are other forms of attention that have something fancier than just a basic dot product. Okay, so then we get these magnitudes, these values coming out of our dot products. We're going to do something with them as well. We're going to look at all the values coming from Q1 with every one of our key vectors for the whole sequence, K1, K2, K3, and so forth. And we're going to pass all these guys into softmax, and that's going to convert all of these into something that looks like probabilities. Some values between 0 and 1, they all add up to 1. They're not really probabilities, right? They're just normalized to look like them. And we're going to use those values to multiply by the value vectors and kind of push these things all together. So we're going to get some influence from all the other words out there, even when I'm operating on a current word. And the degree of that influence is controlled by these softmax scores. All right, so we're moving quickly, but this is review, so hopefully everyone feels comfortable. Any questions on this? Go for it.
Are the query key dot products non-negative, strictly non-negative, or can they be negative?
No, they can be negative, right? So these guys over here, they're vectors. You don't know what's in them. They could be negative components. Their dot product itself could be negative. That's fine. That's why we're doing softmax, though. It's not going to permit any negative values afterwards. Big negative things will just get driven to 0. OK, so let's see the softmax, which is what the question is about. It's basically exactly what we think. We're just going to do a little bit more work on it. We're going to divide by some term. The 8 is some empirical value here. We're going to normalize by something that has to do with the dimensionality of this guy. Really, that's just a trick to kind of maintain the average values of these things. And then we're going to have these softmax scores. These are exactly the things that add up to 1. Of course, normally there's more of them because the sequence is longer. Question?
How do we know is the query embedding and key embedding come from the tokens, or they're different?
The tokens are each going to get assigned an embedding. That's the green guys over there. So x1 and x2, think of them as separate tokens. They each have their own vector. We're going to take these vectors. We're going to do a matrix multiply by the query key and value matrices. That'll produce 3 vectors for each of these words, so Q1, K1, V1. And then we're always going to compare the query with all of the keys in the sequence. Those are all different vectors.
Oh, so query key value is different parameters?
They're actually not parameters. The parameters are those matrices we multiply by. These are just some values that we get. Yes?
Can you please explain why we multiply by 8 the probability again? Why don't we just do softmax directly on the score?
We could, but if we don't do some normalization, what ends up happening is you have one value that's typically much bigger than everything else. So the softmax scores you get are like 1 and all zeros. So what you get is that you get huge influence from one word and nothing from all the other guys. which is basically useless. We don't want that. Cool, good questions. Keep them coming. Any other questions about the operation so far? Cool. And again, the main thing to keep in mind is sort of the way we're doing this process. We're going to start by looking at every word in our sentence, and then we're going to do this comparison of the current word I'm looking at with all the other words. The comparison says I'm looking at a particular query. I make the comparison of the keys of all the other words. So that's what you're seeing here. You're seeing Q1 compared with K1 and K2. But after this, we're going to move on to looking at the second word. We're going to do Q2 times K1 and then times K2. So again, you're doing a total of n squared of these comparisons. Everybody okay with this? And this is the reason why we'll talk about subquadratic things at the end of this lecture. These operations are quadratic in the length of our sequence. Now, no big deal here because the length is 2. But if we had a sentence that had 10,000 words in it, or 100,000 or 1,000,000, then you're starting to talk about a huge number of comparisons. Cool. Any other questions? All right, then we can keep going. So far, we've done nothing except compute these values, 0.88 and 0.12. And what is their interpretation? It's something like this. We are currently looking at the word thinking, and we want to know how much influence we should get from other words. And we're going to encode this influence into, as we'll see, a linear combination of the value vectors for all the words. But the weights in that linear combination are determined by these softmax scores. So over here, when we're looking at the word thinking, we're going to take 0.88 and multiply by the vector for thinking. But we'll also add in 0.12 times the value vector for the second word, machines. Now, if the second word was totally independent and had nothing to do at all with that first word, what we'd really expect to see here is that these softmax values would be something close to 1 and 0. But here there is some influence as captured by this 0.12. Sound good? Now, can I be more specific about what I mean by this influence and like what's going to be in these value vectors? Not really, right? This is just kind of our intuition for how these things should work. All right, let's go ahead and put it together. We're doing these multiplications. We're computing these 0.88 and 0.12 values. And now we have our value vectors that we have not used so far. We take all of the value vectors for the whole sequence, multiply them by these softmax scores. We get V1 times 0.88 plus V2 times 0.12, and that's what gives us the Z1 over here. This Z1 is the output of the attention operation for the first word. And what is this guy? Just this linear combination of the value vectors. That's all that's sitting inside it. Now, same thing for Z2, right? This is going to be the output of attention layer for the second word. And it's likewise a linear combination, but it's going to have some different values, right? What those softmax values are, we don't see it here, but they're dependent on the value of Q2 times K1 and Q2 times K2. All right, kind of a lot of things to keep in mind, but that's roughly what's going on here. Anybody confused by this? Cool. All right, so this was all just a bunch of work to do a single attention operation. And because we're doing it in this kind of vector form, it's a little bit ugly to write it down. So for this reason, we ended up having these nice formulas that we wrote instead. These are exactly what we saw before, except it's being done simultaneously for all of the vectors in the sequence in matrix form. And kind of the full attention operation is just this guy on the bottom. We have 3 inputs, the query, key, and value matrices. You can think of X, which is the input itself, also like an input. And all we're doing here is computing softmax of the things that we talked about, which are the query vectors, now all stacked together in a matrix, times the key vectors, also stacked together in a matrix. You're doing that matrix multiplication. That gives you a big matrix with all these values that we're going to run into softmax. And then we take all of these values, again, in a matrix, the softmax scores, multiply by the value vectors themselves in a matrix. It's a very compact representation. One thing you may want to do is take some paper, write down the dimensions, and make sure that you're actually extracting the correct things you'd expect. In other words, convince yourself that the bottom of this slide is equivalent to the operations we were doing on the previous one. Not super hard, but at least you'll feel confident about what's going on in these formulas. Cool. Questions so far? Yeah.
For the matrices either B, Q, or A, are we taking one row as corresponding to each word or one column corresponding to each word?
I'm not going to tell you. Try it. You'll see what's going on. The starting point, which will determine the dimensionalities for everything, is the x's. The x is a big matrix of the word embeddings, and it's going to be
N cross B.
yes, exactly. Then see what has to happen from that point onwards with all the other matrices. Yeah, this is exactly what I mean by try to recover the formulas and feel good about what's happening in these operations. OK, more questions? Great. So far, all we've really done is design an operation that we can write down in one line. It produces some outputs. These outputs were a sequence of vectors. The x at the beginning is also a sequence of vectors. So all we've really done is transform one sequence of vectors into another sequence of vectors. But this output sequence that we're obtaining, it does capture some notion of things interacting with each other. That's it, though, right? We haven't done any other work for our design so far. Everybody agree? So naturally, this operation itself is not sufficient to do terribly much. We're going to have to combine it with some other things to actually build full layers. But really, this is the key of what makes large language models work. Just one simple equation. And notice that all the components are very ML friendly. So all we really have here are things like matrix multiplies, softmax, that's the only nonlinear thing going on here, and then another matrix multiplication. Everybody agree? So this is like a one-line thing in PyTorch or any other ML framework that you want to do. Quite simple, but very, very powerful, as it turns out. Cool. Everybody still comfortable with this? We're actually not really going to talk about this equation too much more often, so if anybody's confused, now is the time. All right. Let's start building to get to this overall layer. The first thing that we said we're going to do is rather than just run this equation once, let's go ahead and run it multiple times. And the intuition that we had here basically was we don't run a CNN, for example, with just one kernel or just one filter. That would only capture one type of pattern in the image. We want to be able to learn many different kinds of filters to extract the presence of lots of different kinds of patterns. Now, it's a very similar story here. One attention operation, even if we train those three components, may not capture all the things that we want. Let's run it multiple times and then do something with all of the different output vectors that come from these multiple times we're doing it. And we're going to call this thing multi-head attention, but it's literally just taking it and doing it more often. There's nothing else really happening here. So this is the picture once again. We're going to have still our inputs x over there. These are two vectors. In this simplified version, there's two words. And these inputs are four-dimensional, but of course in practice they're larger dimensionality than that. We go ahead and run attention. How many different times here? Go for it. 7? I disagree. 8. Yeah, it's 0 indexed, but yeah, not super critical. Right, so we run it 0 through 7 times, which is 8 times here. Each time, we have separate matrices, query key and value, that each separately produce query key and value vectors for all the words in the sequence. So notice there's a lot of matrices floating around here. We produce outputs. These are the z's from all of these guys. Now, the only question that's left for us is how do we combine running this operation 8 times? In the end, we don't want to have 8 copies of the operation with those outputs floating around. What we're going to do is concatenate all these guys, these z's, and we're going to do another multiplication by some linear layer. That's this w here, wo. And this will produce the output for us. And this output, once again, is just going to be a sequence of vectors. All right, everybody OK so far? So we've added kind of one more set of parameters. Previously we said, let's just take the top row. We'll have these outputs z. Now we have multiple z's. We have one more linear layer, so one more set of parameters. And that compresses these guys back into a sequence of vectors. But otherwise, nothing super special is happening. OK, so we're going to do multi-head attention, that's for sure. We then said there's one more piece that has to get added. And this piece has something to do with sequences. So far, if you look over here, it doesn't really matter too much the order that our elements in the sequence, our words, come in. All of our operations are kind of symmetric, right? I can switch a word's location from position I to position j. Doesn't make any difference, right? It's going to be compared to everything else, whether it's at position I or j. The values will be the same no matter how I flip things. So far, we're not really capturing order. But of course, in actual language, order matters a lot, right? If I permute the words in a sentence, I'll either create nonsense or I'll change the meaning, right? So we want to make sure that we preserve that order. Everybody good with this intuition? OK, so that led us to this idea of let's try to encode the positions of the elements of the sequence into stuff that we're doing here, into something that can take place inside the attention operation. And this led to some pretty fancy stuff. But in the end, we had a pretty simple idea. Let's find some way of taking information about our location in a sequence and injecting it into these vectors that we're operating on. Now, for a bunch of reasons that we talked about last time, we ended up doing this really weird encoding. This encoding says, OK, well, for every single word, I'm going to craft a special vector that gets added to the word embedding. And the special vector contains some information that represents the position I'm at. So the special vector contains information about being at position 0, or at position 1, or at position 2, or whatever. And this thing is a vector, so it has whatever length our word embeddings have. And the way we're going to generate the components of that vector was through this weird formula. Now, what is this weird formula? We talked about some reasons why we created it. It has some special rotational invariance properties and some other things. But that's not the really critical thing. The picture you want to have in your head is just these guys on the right over here. I want to add some information about the fact that my word is at position 37. And based on that information, I'm going to craft, let's say, maybe a binary version of the number 37. That's what you're seeing on top. I'll add that binary encoding to all the places I can inside my word embedding. But when I do these kinds of binary encodings, I can go up and down. So let's create a smooth version that approximates the thing on top. This ends up being the reason for these things. OK, we can ignore the details. Is everybody comfortable with the idea? OK, and in this original version of things, what we do is compute these positional encodings, add them into our word embeddings, and this gets sent through the entire model. We just do it once. Now every single one of my word embeddings at the very input has this special positional information. And whenever we operate on these things, that positional information is sitting in there. So the model is now aware of the fact that there is some order. It cannot ignore that information anymore. And notice now that if I flip the words at position I and j, it does make a difference, right? Because they will now have different positional encodings. And therefore, we won't get the same answer anymore. Yeah?
How do we know that the positional encodings don't scramble the meaning of the embedding?
They could, right? And part of the reason for these fancy formulas is to create something that doesn't cause too much damage. It has to be there. It shouldn't get washed out by the values of the word embeddings. It also should not itself wash those out. So that's the reason for why we're getting values between 0 and 1, and their magnitudes are bounded, and a bunch of other things. It's also the reason for this 10,000. Not really critical, but this value was something that they found experimentally. All right, any questions about the intuition for these positional encodings? We'll do a little bit in the homework about the actual details, so don't worry too much about these. Yeah?
You swap that word with a specific index that happen to be the same weight of that word. Would that just give up the same result?
It's actually designed to make it impossible. You can try it. Now, the sequences are not long enough ever for this model itself for you to go and have exactly the same positional encoding after you flip through. Try it out with this formula and you'll see why that takes place. You can actually try it and say, hey, is there a value of position, like position 1 and position 2, that gives me equivalent vectors? And if you try to solve for it, you'll see that it has to be longer than the sequence length. But you're right, if we go to very long sequences, this actually could happen. So as a result, what we're really doing is not this formula for modern language models. Cool. Other questions? All right, so very briefly, we did talk about how modern positional encodings, by which I mean the ones that we use for the last 2 or 3 years of language models, are not exactly these sinusoidal ones. They're something different. We'll talk more about these, and they're a good choice of paper to present on. The most popular are these things called rope. What they really do is, rather than being added in at the bottom once, is they're multiplicative. They slightly shift things at each attention layer. So you take the outputs from attention, and rather than just keeping them as is, you say, depending on the position, I make some small modulations. I make some small changes. And we're making changes to vectors, right? So one simple way of doing that is to rotate them a little bit. You multiply them by a certain rotation matrix. That rotation matrix you pick, it contains that positional information. So same idea, but it's now multiplicative instead of additive. And you don't do it once at the bottom, you do it in every attention layer. Okay, we're not talking too much about this yet, but again, a good topic for you guys to look at in more depth. Cool, so this is pretty much everything that we did for building up attention and getting it ready for actually building encoder and decoder blocks, which are the things that we'll put together into an actual transformer model. So maybe let's take 2 minutes. This is all review. You guys can ask me more questions. Otherwise, feel free to take a break. Yeah?
This specific formula for positional encoding that we just saw, that's just strictly added to the vector?
The sinusoidal ones, yes.
Yeah.
And specifically, they're added just to the word embeddings.
Okay.
At the very bottom, once it's in there, it's always there, basically, right?
Yep.
Every operation you do going upwards is going to contain them.
Okay.
But we don't do it again.
Yep.
Yep.
Wait, just if it's adding the coding to the sequence, right? Won't that information get lost as soon as like you scale up the model and you add it? Like let's say like a really big transformers will have like a lot of blocks, so then it passes through that like L times. Won't that encoding information get lost?
No. So you're always operating on the original embeddings. Of course, I mean, if you do a bad job of training, then you could end up getting all of these activations that become 0 or infinity. That'll destroy everything, both positional encodings and the original word embeddings, right? So you always have to have stability as you're running through the layers. But that's also true in general, even without positional encodings, if you see what I mean. These guys are in there, and these formulas create magnitudes that are preserved as you keep operating through it.
I'm still
Well,
confused.
so you only want to keep in mind, because I'm not even showing you the formula for it, the kind of high-level details.
Yeah.
Previously, we said for every word embedding, we're adding in one vector, and that's it.
Yep.
This time, we're saying we're not adding anything. We're going to multiply, and we're going to multiply each time we do an attention operation. Okay, and how do we put that information? Previously, the information about position was sitting inside these things we're adding in. Now it's sitting inside these matrices that rotate. So if I'm at a certain position, I rotate my vectors by a little bit. If I'm at a different position, I rotate them by more. So think of saying, hey, I'm going to rotate my vectors by 1 degree, 2 degree, 3 degree, 4 degree, whatever, based on my location. It's literally just that.
So when you say we don't add it, we inject it in the attention.
Yep.
How do you back it?
Literally through a matrix multiplication that slightly changes the angles of your vectors. So let's say your word vector is pointing this way. Now, if I'm at position 1, I move it slightly to here.
Yeah.
If I'm in position 300, I move it to over here.
Like, why is this better than the original?
For a bunch of reasons. It's much more stable. it's much easier to actually go implement this. It doesn't get lost as you go through the layers in the same way. So there's a bunch of like empirical reasons for why this is pretty good.
Then what? Okay, sorry.
Yep.
One last question.
Feel
What
free.
if we want to inject every attention layer?
So that it's more difficult to lose the information. If you do it each time, it's always there. You don't have to worry about as much as about the training dynamics that could lose it potentially.
Thank you.
Yep. We don't actually. Although we could do that, in practice nobody does it that way. It doesn't really bring any benefits. What we're going to do is train them as well. So we're going to make all of those word embeddings trainable parameters. We'll initialize them to something random. And then as we train the entire model, we train those guys as well.
If we say we have 5 images, so let's say we have a dimension of 512,
Yes?
then we'll just put random values for every word.
Yep. And then we'll train them. And eventually, we'll have word embeddings, right? They'll be trained to be located somewhere useful in the space.
But how the embedding into the word?
It contains information about the way that words are going to be used downstream. So if we're doing translation, like the Transformers paper, you're getting representations that are useful for being translated between whatever pairs of languages. If we're doing just language modeling, then very generic representations that are useful for whatever task. I can't say more than that. It's not like there's some super desirable property that I'm guaranteeing will be in there. But typically they actually behave pretty similarly from what I've seen to what you'd get if you ran Word2Vec, for example. A lot of those famous analogies, you can actually find similar things for these embeddings as well.
Why tokens and why not words?
Oh, well, you can't really, you could try doing words, but the problem is like the vocabulary for words is first huge, and second, you have to think about like, how are you going to do it, right? Like some words are really just combinations of other words. Are you going to keep them separate or are you going to break them down? Like tokenization just answers this question basically. There's a bunch of rules. These rules themselves sometimes satisfy some properties, sometimes they're just kind of heuristics. But each different tokenizer has these rules that it follows, and it produces particular things. Now you might say, okay, well, what if my tokenization is not optimal, right, for my task? So there's some new research that tries to learn the tokenizer end-to-end inside the model. But it's not clear yet that it actually works better than like very standard tokenizers from the past. Yep. Yeah, and this is like classical NLP. Like these were designed 20, 30 years ago plus. And they're still pretty good. Go for it.
So in rope, if you're rotating the vector same space as the embeddings themselves,
Yes.
isn't it possible for one word to become another word if you rotate it?
Yeah, so these matrices, the rotation ones, are designed not to move things too far, right? So that's your goal here. And your space of how much you can rotate is pretty big, right? Like it's not just a plane here. We're talking about a very high dimensional space. But yes, like how much you rotate is never like a huge amount. And the chance that you'll accidentally flip over to something else is very small.
Is that the same way with the sinusoidal embeddings?
Same, yeah. The sinusoidal ones are also designed to basically do that, right? Like the actual magnitudes inside the positional encoding is very, very small on purpose, right?
Thank you.
Good question. Yes?
Clarify my understanding. Is a position embedded the same when we're calculating each word in a sentence, or do we calculate like based on the relative position between two words in the sentence?
So you're actually designing a lot of these for those things to be the same.
Okay.
And especially rotational ones actually do take into account relative position. Those sinusoidal ones, they're based on absolute positions, but also like it's designed in such a way that the gap between I and j is the same as I plus k and j plus k, which is why we had all the sine cosine business as well there. So you're getting these kinds of properties that you want basically.
Okay, so like it takes account into the relative position, but
Exactly.
at the same time you don't need to do it multiple times to add to the computational power.
Yes, although the computation issue is not really a big issue.
Okay.
Like multiplying by some matrices once is not a big deal. Even if you do it once per attention layer, it's also not a big deal.
Just just considering how many times we're calculating attention, like that's actually a big deal.
But the big problem there is the quadratic complexity of those dot products. Not doing something to each vector, right? That's an O of n thing versus an O of n squared thing. So you're not really too worried about like rotational encodings. Yeah.
It's like intuitionally, if you like shift entire sentence by one word to the right, it's not going to change that much because the positioning pattern is designed to be like
That's exactly right. Yeah. But again, doing this through the math rather than like guaranteeing that shifting by one will not change anything or things like that, right? But yeah, you have the right idea. All right, let's keep going. So this is kind of where we left off last time. We started talking about this idea for an architecture. And again, we are really doing translation. So we're not even building a foundation model yet. We are just kind of going back in history and looking at the first transformer model. And that is a translation model. Its input is a sequence in one language. Its output is that sequence in a different language. OK, so we're not really yet doing anything with self-supervision or anything like that. That's why you want to keep in mind this particular architecture. Encoder-decoder is very natural, right? What are we really doing here? We're taking a sentence in one language. We want to transform it or encode it into some space that carries the meaning of the sentence, but it doesn't have the actual details of the language. And then from the sequence in that space, we want to decode it to bring it back to whatever language we're translating into. So that's the basic idea for encoder-decoder. And of course, this is not just an architecture exclusively for translation. Encoder-decoder architectures are used for just about everything you possibly want. Everybody comfortable with this idea? Cool. OK, so as before, we're going to use attention, so no recurrence. And let's go ahead and actually start looking at this architecture that we've seen. We kind of already understand more or less everything that's going on in this picture. But let's at least remind ourselves of all these different elements. OK, so let's start going through. We're going to have this very simple, kind of more abstract picture. If you look at this, it's actually the same thing as the picture from the paper. It just doesn't have all the details. But you want to look at this one first to have a sense of the way we're going to have data flow through the model. So when I'm doing a forward pass, I will start with my sentence, which is a sequence of words in one language. Here it's French. I'm going to start that, go ahead and plug it in. It's going to run through a bunch of encoders. Each encoder's output becomes the input to the next encoder in the stack. And then eventually, I'll hit my last encoder. There'll be some output from that last encoder. And now the interesting thing is, again, as I mentioned, this output, although it's still a sequence of vectors, it carries a lot of information in some very abstract way that's not directly connected to the actual original language. And I want to keep that information. So now for my decoder, I'm going to make a change. Instead of being connected just to the output from the previous layer, I'm also going to add in a connection from the top of the encoder, from this last and most abstract representation of the original input. So that's what you're seeing here. All of these decoders, yes, they're taking an input that's coming from the previous decoder, except for the very first one, of course. It doesn't have that. But everybody else is also getting information from that top encoder. Everybody OK with that? Go for it.
While passing from one encoder to another encoder, are they adding positional encoding again?
Actually, we're going to do it once at the bottom. And that's it, as before. OK, so we're going to have to make a change to the decoder architecture compared to the encoder. Because again, we have these two inputs. So it cannot just be basic self-attention in the way that the encoder is going to have, because we have some other input altogether coming from the last encoder. So we'll talk about that change. And then finally, we'll get to the very last decoder as well. And this decoder is going to have to produce output. This output being the sentence in this language that we're translating to. There will be a few extra steps for producing the output itself. But that's kind of the high-level picture so far. Does this sound good for everybody? Cool. OK, now there's one more interesting thing about the decoder that's also worth thinking about. The decoder is actually generating words as we go. It does not have access to the full sentence the way the encoder does. The encoder gets input to a whole sentence, right? It can look at all of it. And when we run attention, we have access to the whole sentence, right? That's how we made all of our comparisons between the query vectors and the key vectors. For the decoder, we do not yet have access to all the future words we're going to generate, right? They don't exist yet. We haven't created them yet. So we're not going to be able to run self-attention fully. We'll have to kind of mask out stuff in the future that has not yet been generated. We'll see this in a second, but does that intuitively make sense for everybody? Again, that's the big difference here. Encoder's processing a sentence that's already there. We have all of it already. The decoder is also processing something. Yes, it has the inputs from the encoder, but on the other hand, it also has to operate on its own sentence that it's creating, and it doesn't yet have access to the future. So it can't run self-attention in exactly the same way. Does this sound good? This is a very basic causality principle. It's actually not that unusual. You'll see it in signal processing all the time. There are non-causal circuits and filters. There are causal ones that have no access to the future, and so forth. OK, let's start taking a look at all these guys. We talked about the encoder. We know one thing inside the encoder is self-attention. That's the thing we've been talking about the whole time. We're going to add one more element to it, and that's just going to be a very basic neural network, an MLP. And what is it going to do? It's just going to operate on all of the output vectors that come from self-attention. So self-attention was giving us these vectors that we talked about, these z's, and there was one of those guys for every single word vector. And now what we're going to do is operate on all those guys individually. So really, we've kind of divided the work that one of these layers has to do into two pieces. One piece that's doing interactions between words, that's self-attention, and one piece that's kind of working on every word separately. And that's a feed-forward neural network, or MLP. Is that OK for everybody? All right, so why do we actually even need to have the feed-forward neural network? Think of this as a similar kind of thing that we saw in CNNs, right? We're getting more and more abstract information, so we have to transform all of these vectors from our words, all of these representations, again and again and again, each time trying to get the underlying meaning, rather than whatever lower level details of language, et cetera, that were originally in there. OK, and then later we'll design our decoder. And here's the big change that we talked about. We're still going to do self-attention. That self-attention will operate on the sequence of translated words that we've created so far. But then we also want to do some kind of comparison with the output from the top encoder. That contains all the meaning. And for that, we're now doing attention, but not on the sentence itself. We have two different objects to do attention on. So this is a form of what's called cross-attention. And this cross-attention says, OK, give me the encoder sequence and the sequence I've generated so far at the decoder, and let's compare those two things. Now, there's nothing stopping us from doing this. We're just saying that the query vectors and the key vectors do not belong to the same words. They belong to two different sequences. But the operation is otherwise the same. So it's no longer self-attention, where we're applying it to words from the exact same sentence. It's cross-attention, where we're applying it to words from two different sentences, one pertaining to the original sentence, but really it's contained in the encoder output, and one pertaining to the decoded sentence, which is the translated one. All right, everybody OK with this idea? So why are we doing this? Well, the basic answer is we don't really want to forget what's relevant in our original sentence. If we were to just pass through a bunch of self-attentions in the decoder, there's a risk that we would increasingly lose track of that original information that we cared about. But by continually passing it in and running cross-attention, we're much less likely to forget about that. All right, does that sound OK? OK, let's see some of the details. These are just general blocks, but we can actually look inside them as well. If we look at an encoder, it's almost exactly what we talked about. Here's the two pieces that are the important pieces. Self-attention. And again, this operates on all the words at once, because it has to do interactions between words. And then the MLP, which, as you see here, operates on every one of these outputs separately. So there's no connection going on between Z1 and Z2, two locations in our sentence, when we pass them to the MLP. That's the big difference here. Everybody OK with this? OK. Okay, now we can make the story a little bit more complex. We're going to do a little bit of deep learning tricks. These are more for stability, for training, than anything else. They're not really key elements. They're just things that happen to be useful. This really gives you all the information for an encoder. I have two vectors, x1 and x2. As we mentioned, we're going to add in the positional encodings, which are over here. Pass these guys into self-attention. And then I'm going to do some normalization. And I'm also going to do a skip connection. And if you go back to learning about CNNs, you'll recall how skip connections, residual connections, these things are helpful for training. That's all that's happening over there. And once I've done this, I go ahead and run my MLPs on all my vectors. I do another skip connection and normalization, and I'm done. Does this sound okay for everyone? Cool. All right, there are details that we could talk about for what the normalization looks like, although it's not super, super critical. But we kind of now have a pretty solid picture of what the encoder looks like. And in fact, we can start looking at the decoder as well. It's not too much more complicated. Almost the exact same kind of thing, right? It's just that now we're going to have this additional cross-attention encoder-decoder layer. Otherwise, it's exactly the same thing. Nothing super interesting going on. You're getting your k and v vectors from a different place than you were before. OK, let's start talking about the more fun part. How do we create an actual output sentence? Well, it's going to be very simple. We're going to take the very last thing the last decoder generates. We're going to have another linear layer. This linear layer will then produce a vector that's as long as our vocabulary is sized. And it's going to have some entry in all of those positions for my vocabulary. OK, and then we're going to run softmax over that. It's almost as if we're classifying a particular word. The softmax will give us probabilities. Now we have probabilities for what the word should be at this position. And then we can use any kind of decoding rule that we want. We could take the highest probability value, and that would produce for us a word. It would just give us an index into our vocabulary and say, OK, well, this is the word that we got. So if that index in this case is 5, the word could be am. I think the sentence here is I am a student, so this is like the second word. So this final part is almost exactly what you do with your CNN when you're running a classifier. You're just going to go ahead and have a linear layer. You're going to run softmax. And then finally, you're going to pick your class that has the highest probability. Or something else if you prefer. All right, this sound OK? So now we can kind of see the full picture. Let me go actually back to where we introduced the picture from the paper. You can kind of see exactly what's going on with all the pieces. We have our original input sentence. We take that, we tokenize it. We now have a sequence of tokens. Those tokens, we get embeddings for them. We add in our positional encodings. It has that little sinusoid that you're seeing over there to remind you of what that looks like. You go ahead and pass this into your encoder layers. That's what's on the left. You're seeing one encoder layer. We know the two key components of an encoder are self-attention and the MLP. So that's what we're seeing over there. We know that we're going to do skip connections and a normalization for each of those two things. And that's a full encoder. Now, we're not going to do this just for one encoder. We're going to stack them on top of each other, the same way that we do in deep learning in general. We're going to do n of those guys, so you have an n times on the left over there. And that's the full story of the way that the data flows through when we're going through the encoder. OK, and then we take that output. We go ahead and pass that output as well into the decoder stack, not just to the very first encoder, but to all very first decoder, but to all of those decoders. And we're going to do the same exact kind of thing. For the decoded sequence, we're going to have as well some embeddings. Again, notice that these embeddings are different from the original embeddings. We're translating into a different language. So we're going to have different words here, and therefore different embeddings. But we're going to do exactly the same kind of thing. Take embeddings, this time for the output. Go ahead and run positional encoding through it. Go ahead and pass it into our decoder. We're still going to do self-attention, but it's masked. Why is it masked for the decoder side? Well, we do not yet have access to the future. If we haven't generated those decoded tokens, we don't know what they are. We can only do self-attention on the sequence as it is so far. If we so far translated 3 words, that's as much as we can do self-attention on. But when we generate a 4th word, we'll do self-attention on the 4th word sequence and so forth. So we're going to run this process. We have mass self-attention. And then we keep going. We're also going to have cross-attention, which takes the output coming from the encoders with the decoder, compare those two. And then finally, we'll do MLP again. We run n of these guys as well, pass into a linear layer. The linear layer is just telling us what words we should generate. Run softmax, get our probabilities, select our words. Pass it back into the decoder, and keep generating the sentence as we go on. All right, this sound good? And this is it, right? This is the full architecture with basically every detail taken care of. What we're going to do after this is basically start changing things. This really makes sense for translation, and it performed incredibly well, which is why people studied this architecture so much. Now we're going to say, hey, I don't care about translation as a particular task. What should we modify to make this work for other tasks or for use as a language model or a foundation model? Cool. Go for it.
For the decoder or encoder decoder retention, do we have the weight matrices out there to cater the outputs that are coming from the decoder and generate the key value of that?
Yes, the decoder has its own weight matrices. So I have weight matrices for the encoder and the decoder. Both are trained. I have access to both of them.
And the vocabulary size out there in for the probabilities and the input dimension, those two need not be same, right?
No, because our vocabularies can be different, right? We have two separate languages here. Cool, great questions. All right, so this is pretty much it for transformers. We now understand all the low-level details. We will have a homework assignment where basically we're going to implement a lot of this stuff. We're really going to do it more in the language model sense than the actual translation task. But we'll get into a lot of the nitty-gritty details. However, it's not too complex, right? This picture looks kind of like a lot initially, but the actual basic building blocks are fairly simple. All right, let's kind of get back and talk about what we do in the future. And then in the time we have left, I'll mention the subquadratic architectures. Here's kind of what we said. We have the full architecture. We're going to talk about how to use it pretty soon. We'll talk about how to train it. Well, it's going to turn out to be very simple. And then we'll soon start removing parts from here. And it's going to turn out that removing parts will really do a lot of what we want. I do want to take a second and talk about how to train it. It's actually very simple. It's almost exactly what you'd think. You are going to take a big supervised data set. The supervised data set says, I have pairs of sentences that match up to each other, sentence A in one language, and the translated sentence B. And then I'm going to train by saying, for sentence A, I should obtain sentence B. So it's exactly the kind of loss function that you'd expect. You're basically going to run cross entropy on each of these elements that you're looking for. So this is supervised learning. We spent a bunch of time talking about how supervised learning has these deficiencies, and we're going to move past it to self-supervised. Notice that the original transformer is not self-supervised. It's just basic supervised learning. It just happens that we're lucky we have a ton of data, right? People have translated a lot of different pairs of languages, so we have plenty to train on. But we're going to soon move past this. When we start building language models, there isn't going to be supervised data that we can use. We are going to have to do everything self-supervised. And rather than saying, hey, I want to predict this entire sentence from language B for this input for language A, we're going to say things like, hey, let's predict the next token in a pre-existing sequence of tokens where we know what the next token is. So that will be a little bit different, but of course the spirit of it's pretty similar. All right, any questions before we jump to the next part? I actually think we have a break, so feel free to ask me more stuff for the next 2 minutes. Sorry, let me answer this one more.
So here you just mentioned that we perform the embeddings in every text layer.
Yep.
But here you said that we only perform it.
Yes, so this is the original transformer. It has these sinusoidal embeddings. These get added to the embeddings at the input and output side, but nothing else. Now, for modern language models, people do it differently. This picture is not operative anymore, right? This is just the original translation model. So in that case, we're not going to have that sinusoidal position encodings. We're going to do something different, and we'll be in every layer. Yeah, so we'll see more of that when we talk about these other language models. They do deviate a little bit from that picture over there.
So the vocabulary size here is just all the number of vocabularies in the program.
Yep. Yeah, so this could be 100,000, for example.
Okay, so they just particular probability
of each word that might.
Exactly. Yep. Yeah, for the current vector I'm looking at, to decode it, I compute the probability that it pertains to any of the possible elements of the vocabulary. Yep.
So for the neural network part, I'm a bit confused if it's completely disconnected per term or per attention head.
No, we've already collapsed the attention heads together. So the outputs that we're getting, right, we concatenate all the attention heads, we multiplied by that common linear layer, and this gave us one output for each of the elements of the sequence.
So
we have one vector per.
So everything that's coming out of the attention heads does get connected by a linear layer.
Yes, exactly. So I still have just exactly one vector per element in my sequence, and this thing, I'm going to pass it through my MLP. It becomes the input to that MLP. And notice one thing that's kind of confusing when we draw this picture is you might think, oh, there's multiple MLPs, that I'm training one for each possible element of a sequence. No, it's just the same guy. We're applying it to each of those terms. Okay, let me go here, here, and then here. Yeah.
So we are saying that we are masking the words first in the decoder and then calculation.
Yep.
So initially, like, we have all the mask tokens, right? We are prepared in a token, and in the next step, for that token, and rest of them are mask tokens. So what did affect the self-attention? Because it see that the most important token is.
We're only masking stuff we don't have access to. So we're masking the feature, right? But initially, sure, we're going to have some start translation token. We're going to do self-attention on it. There's nothing interesting going on, right? We're going to generate the next token from this. Now we'll have two tokens, right? We'll do self-attention on those two guys. Keep going, right? Generate a third token, and so forth. We don't have the entire sequence yet, right? We only have the words that we've translated thus far. There will be one such word, 2 words, 3 words. Not yet. We don't know what it is yet, right? We don't yet have any of the feature, so I do not know what those embeddings will be. So for example, if I've translated 2 words so far, I don't know what the third word is. Yep, because that's all we got. There will be future words, potentially lots of them, but I don't know what they are yet. I don't know what index they have in my vocabulary. I don't know what word embedding they have, right? So I have to mask all this stuff out completely because I have no information. I'm only not including the feature. That's it. Yes. Well, not really dropping it exactly. Like, it's not like I have it, right? I haven't generated the feature tokens yet. I don't know what they are, so I can't use them, right? So it's not so much that I'm like not including them. Yes. Yep. We actually don't do anything. The sequence of tokens, we look at it and read it. We can do some post-processing if we want, but that's outside the model. So we're going to do nothing there. But these tokens are really, they look like parts of words, right? And we just produce them. Too bad, right? That's my basic answer there. Now, sure, that's unlikely to happen because the way we're generating the next token is influenced by what the previous tokens are. Again, that's a self-attention part, right? Each next one is going to look at what happened. This does not guarantee, though, that the output is coherent. You could get an incoherent output that doesn't make any sense. That's still possible, right? That's a matter of how good my model is, etc. But I can get a garbage outputs, and there's nothing to be done about it if that's just what I got. We can do additional things on top, right? But that's sitting outside this architecture. Here, we're getting the sequence of tokens at the output that we have. Anything else you want to do is some additional steps.
Output that we input the decoder.
Yeah, so over here, initially we have nothing. We're going to start with some, hey, begin translating kind of thing, right? And then we're going to generate a token that's part of the first translated token that will come out to the top of this guy. Then we're going to take this guy, put it back in here, right? And we're going to take its embedding. So I've generated a token. The token is something, right? I'm going to go back in here, take the embedding for that token, add its position, which is the first position, pass it through. Right. Then I get a second guy, and now my output embeddings have first word, second words embeddings.
This is like the first part of the sentence we have translated.
Yeah, exactly. Yeah. And of course, I need to operate on their word vectors as well, so I need to use their embeddings.
Oh, I see. What do you mean by mask? In my understanding, the mask means like we hide the part we haven't translated.
Yes.
Yeah, but since we have put only the part we have translated as an output, we still need the mask here.
Yeah, because I don't know the future, right? I don't have access to. I've generated 2 words so far. There's going to be a third, a fourth, a fifth, etc. But I don't know them yet,
yeah,
right?
I mean, we have removed the future information.
Exactly.
In the output part,
It hasn't been created yet. So I have to mask it away, right? I don't have access to a full sentence at the output side yet. I only have access to the beginning of it, however much I've generated so far. Everything that's not yet generated, mask it.
Oh, I mask out the structure, not the information in the sentence.
We don't have it yet, right? So we can't use it. Therefore, we mask it. Yep. There was one more question. Yeah.
So, just a preliminary question. So, we can parallelize the feed-forward MLP, and we can do parallelization operations on the multi-convention.
We can, yes.
Okay.
But what we cannot parallelize, at least not in a very easy way, is just self-attention within a head, right?
Okay, so we can't parallelize an individual attention operation. We can't.
Yeah.
Okay, that makes sense. So,
Oh, sorry. I said that in a confusing way. Even that we actually can, although it's not trivial because we do have to do everything, right? We have to compare everything with everything else. But that's like n squared things. I can do those at once. Yeah. The one thing that's really not parallelizable is over here. Because even if I could do that on this side, here I haven't generated anything, right? To work on the next element, I have to wait for the current one to be generated, and only then can I move on. So that's inherently serial at the decoder side.
that makes sense. Okay, so that leads into my actual question, which is I read the potential all-you-need paper, and they keep emphasizing that it's better than RNNs time-wise because it's parallelizable and the RNNs aren't. But I mean, you do this n times and you have to wait for the output every time. It seems sequential and almost even worse in time of like.
It actually can be worse in a lot of ways. So yes. Yeah, I mean, depending on what you're doing, you can do a bunch of things in parallel, but here you're stuck, right? So there's an inherently like linear thing that you have no choice but to do here.
Yeah.
All the rest is more like if I do these n squared things faster, can I go faster? But that's it.
So is attention, are they trying to say it's, because they keep also emphasizing that the worst part of the attention isn't quadratic.
Yeah, exactly.
But are they saying that it's quadratic in compute power, but in time it can be parallel?
Yes.
Okay, I see.
Yeah, you have no way of skipping the actual computational complexity, but if you can parallelize, you can do that, right? Because over here on this side, right, I have to compare every word's query vector with all the other words' key vector, but this does not affect these comparisons for the next word. So if I could do all those words in parallel, right, if I have the compute for it.
Okay, so I should think of it like, although these n operations exist, those are, I can think of that n as sort of a constant almost, right?
Yeah,
It's like,
because they don't affect each other. Yeah, exactly. Well, not really constant though, right? Because there's a lot of them,
Yeah,
right?
sure.
And that depends on the length of the sequence, right? So if I make my sequences longer, it's not constant.
But the time power is strong with respect to the n.
Yes.
Okay, that makes sense.
But this is also like why, yeah, like this processing is always very cheap compared to this processing. And even when we get to language models, processing the prompt, which is fixed, right? It's kind of like an input sentence that I'm translating, although I'm not doing translation, right?
Yeah.
That's very fast. Whereas this part, I have to wait for the next token. So it's always much slower.
Well, the compute power should be about the same, right? Just the time is slower.
Yes,
Okay,
that's
that makes sense.
that's correct. Yes, but you see what I mean? Like stuff can be parallelized or not, and yeah,
That makes sense.
yeah,
Thanks so much.
you're right. Yeah. All right, let's keep going. We're gonna run out of time as usual. All right, so the thing we've been discussing, including in the questions, is what is the bad thing about attention? And what we said is, well, in attention, in fact, in all of the self-attention layers that we ever do, I have to compare for every element in my sequence, its query vector with the key vector for every other element. And I do this for every word. So if my sequence is of length L, then I have to do L squared things. And this means that I'm doing a lot of operations if I'm trying to move up to very long documents or sentences or whatever. Okay, so one question we might say is there a way to do better than this? And one thing that people often will do is they'll actually go ahead and plot out what these attention matrices look like. So this picture you're seeing over here is basically saying, hey, let me look at the result of that dot product for every position with every other position, right? This query key computation, I can just go ahead and plot it. And not too surprisingly, there are certain patterns, right? For example, the diagonal is pretty bright. You get large magnitudes on that diagonal. That shouldn't be shocking, right? Because every word tends to influence itself quite a bit and matters to itself. You're also seeing sort of other kind of like submatrices. You could think of those potentially as a bunch of separate sentences, right, that I've put together. Then each sentence should have some kind of submatrix that looks a little bit like the overall full matrix, and so on and so forth. So we could have some structure here, and there's a ton of work potentially for how you go ahead and either structure these matrices or compress them or approximate them in a way that doesn't take this full quadratic complexity. This has been done, although not super effectively, although recently it's become more and more powerful. Let's go ahead and start thinking about ways that we can maybe skip this altogether. Okay, so here's kind of the types of values that you should be keeping in mind. If you look at older language models, they really did limit you to a pretty small number of tokens. So it wasn't crazy to have 4,096 tokens, which is still kind of a long sentence, but not a book, right? If you wanted to do a book where really you could have millions of tokens, then maybe you're stuck. You couldn't do it. Now, very new language models can handle this, although not very well, as we'll see. So let's start thinking about some potential alternatives over here. And I'm going to talk about a couple of pretty popular different models that are called subquadratic, because they don't have this full attention quadratic complexity. So let's take a look at a couple of these. And let's go back to something that actually does look a little bit like an RNN. And this is really going to come from signal processing. So let's work with these equations. OK, so what's happening over here? First of all, this is not a discrete sequence. These are continuous signals in time, right? So that's why you're seeing things that are indexed by t. T could be any value of time. Now, those of you who come from EE or ECE have seen these kinds of equations before. What's happening here, I have a state xt. And what I'm seeing on top of that equation is just the evolution of that state. So the derivative of the state with respect to time, that x prime of t, is equal to the following computation, some operator a applied to x of t. So this is how the state evolves by itself, plus b u of t. U is the input here. So my state evolves based on whatever my state's at, also impacted by some input. And then finally, I have this output y of t. It's based on the state as well as on the input itself. OK, so a couple of equations. One is tracking the state. One is looking at the output. Nothing too special here. Now, one thing that's kind of annoying here is this d. I can kind of get rid of it, right? I'm saying the output is also influenced by the input, but who cares, right? We can kind of wrap that into the state directly, or you can think of it as a skip connection. OK, so over here, the state can be higher dimensional. Let's say the outputs are one dimensional, whatever. Doesn't really matter. Let's translate this from continuous cases to something discrete that we can actually work with. Here is an extremely simple kind of model. I have my state x at time k. Time is now discrete. It's a sequence, 1, 2, 3, up to k, and so forth. It's no longer continuous. I have the same kind of thing I've seen before. I have some linear transformations, but my current state is influenced by the previous state and the current output. And then, of course, my output is based on the current state. So this is a lot like an RNN. Actually, it's linear. It's not too different from what we saw before. Nothing special is happening here yet. OK, now let's do something kind of weird. And let's take a look at what's going on. Let's suppose that I take this equation, and I plug in values of k, and see what happens. In other words, let's start building it up. Let's plug in k equals 0. Then let's plug in k equals 1. Then let's plug in k equals 2, and so forth. OK, so here's what happens at 0. Well, there's no previous state. So the state x0 is exactly given by the input that I'm getting at time 0. That is this bu0. Okay, and now my output is always c times my state. So I take my x0 and I multiply it by c on the left to get y0. Just plug and chug. I'm using the rules of those recursions that I've created. Okay, now let's see what happens for state 1. I know that the state is equal to the previous state multiplied by something plus the current input, right? That's what I'm seeing over there. It's x1 is equal to a times x0. x0 is this bu0, so now I have x1 is a bu0 plus the stuff from the current input, which is bu1. All right, everybody following me? I'm just plugging stuff in. It's just algebra. Not doing anything interesting yet. Okay, and I know my output is just whatever my current state is multiplied by c on the left. So it's literally c times x1, which is cabu0 plus cbu1. All right, everybody okay with that? All right, let's keep going. Another longer equation. Okay, my x2 is equal to a times x1, which is aa, or a squared, bu0, plus abu1, plus b times the current input, which is u2, so bu2. And y2 is exactly that with c's everywhere. Everybody agree? Okay, so I'm plugging and chugging stuff in. I'm just following the recursion from its starting point again and again and again. But in general, I'll get the following form. Let's look at this output. It's always going to look the same. It's c times a now raised to the kth power, because it's like a times a times a times a each time, times b times u1, plus the same kind of thing, but with a lower power for u2, u3, and so forth. If you can look at this thing, it's very easy to derive it from just that starting set of steps over there. It's literally me saying, hey, just unroll your recursion so that it goes back to the beginning of time and see what that formula looks like. All right, any questions about this so far? Is there anybody not following what we're doing? It's kind of the thing you do in 7th grade, right? Like you learn about a recursion, and the first thing you do is you say, okay, let me take the current recursion, plug it back in to look at the previous time step, and keep doing it. And normally you don't get anything out of this, but in this case there's something interesting that's happening over here. This last equation that we've written, which is that yk, the current output at time step k, if you look at it, it's dependent on, well, a bunch of these transition matrices. But if you look at what's going on with the inputs, it's some transition matrix combination times the input at time 0, plus something times the input at time 1, plus something times the input at time 2, all the way up to something times the input at time k, which is the current time. So that's pretty interesting, right? We're seeing that the current output yk is really something that looks like a linear combination of the inputs at time k, k minus 1, k minus 2, all the way back to the beginning of time, the very first input, u0. Everybody agree with that? Now, of course, this linear combination is controlled by these transition matrices that have a particular form. There are names for these things, but they're always very consistent. It's c times a raised to however long it's been times b. So if it's been k steps since the input 0, it's a to the kth power. If it's been k minus 1 time steps, it's a to the k minus first, and so forth. It's a very simple, consistent formula. Now, suppose I take all of these transition matrices, these things in the linear combination, let's just think of them as some values. Then what we have here basically is a convolution. Everybody agree? Now, that's all that's really happening. I'm doing a convolution of two sequences, really. Now, sure, the sequence has some very specific structure for what I'm convolving the input with to get to the output. It's this CAK, B, CAK minus 1, B, blah, blah, blah. But that's what's going on, right? Just a basic convolution. Everybody agree? Now, when I say it's a convolution, what I'm saying is that if you write these formulas for yk and yk plus 1 and yk plus 2 and so forth, you're just shifting that vector to CAK, CAK minus 1, blah, blah, blah. Right? You're shifting it over one time step each time. So I have this big convolution between a fixed sequence and my input sequence, and this is what gives me my output sequence. So it's like I've built a convolutional layer here, even though this thing looked like a recurrence to begin with. But it's a very weird convolutional layer. All those filters that we're used to in CNNs, they're kind of small compared to the input. Now, granted, these are 1D, not two-dimensional the way you're used to for image processing. But even if you're thinking of the 2D versions, right, you're moving this small little filter that's a little square around a much bigger thing. Right now, it's like we're taking a thing that's as big as the original image and moving it around, right? So it's something that's a little bit weird. We're going to see that this is actually OK. There's still going to be a way of computing this very, very efficiently that's faster than the quadratic complexity that we get from a standard attention operation. So we're going to work a little bit on this very simple formula, this convolution. Y is equal to this k bar, which is that sequence I'm showing you, times the input sequence. OK, and then can anybody guess how we're going to make this computation efficient? This is really a question for the EE people. How do you do fast convolutions? Oh, there's nobody from EE? How sad. All right, go for it.
I have some guess, but A to the power of K has some, like it's time invariant, like it's going to be like a fixed matrix or something like that. I'm very...
That is true, but that is actually not what we're going to do to make it efficient. All right, it's a fast something something algorithm. What is that thing? Yeah, go for it.
Fourier transform.
Yeah, exactly. We're going to turn out that we can do this efficiently with FFT. Instead of quadratic complexity, it'll be L log L instead of L squared. OK, but we're already out of time. Let's stop there and talk more about this on Thursday.